So the next topic of our lecture is pasteurization and sterilization. And within that, we would be looking at what are some of the advances that has happened over the last couple of decades in retard technologies. So as you know, pasteurization and sterilization, we could have thermal processes or we could have even non-thermal processes. But the focus of this lecture would be thermal. We would have other lectures where we would cover non-thermal pasteurization and sterilization. So as you know, all pasteurization is a mild heat treatment, less than 100 degrees C, usually between 70 to 95. We inactivate enzymes and kill selected pathogens, not all. Depending upon the process, we make a target pathogen, and then we design a process for that target pathogens. In terms of the spoilage microorganisms, we do not kill everything, but we reduce the number significantly so that we are able to store them of our intended shelf life. And then we wanted to make sure that we have minimal changes in our food quality. This is a slide showing you for a low acid product and high acid product. So this is a high acid product such as beer and fruit juices, and the low acid product, high pH product. The purpose for pasteurization is different. Then there are secondary purpose, that's also kind of a different. And the minimal process conditions as listed in this table are different. Why they are different? Because based on that certain processes are developed. So in terms of your main target pathogens, you would have a same effect. But depending upon the instrument technology we have developed, we operate using different processing condition, and then that results different level of quality changes. That was mostly guidelines for the US, but Europe has slightly different guidelines. They consider pre-packaged chilled foods. The guidelines they have that, so this is specifically for pre-packaged chilled foods. They consider either Listeria 6D reduction, which is 70 degrees C, 2 minutes, and that gives you shelf life of less than 10 days at 5 degrees C. And the other pasteurization process is a 6-log reduction of non-proteolytic CBOT, where the process conditions are 90 degrees C, 10 minutes. And that gives the shelf life of 6 weeks at 5 degrees C. Do you know why do we have these two different processes?
Because the composition of the food change, so we have.
For example, the first process where Listeria is our bacteria for the process design, and we say the shelf life is less than 10 days. Why not 11, 12, 14, 15 days, 20 days? So if you design a process where you target Listeria, you are not killing anaerobic spores such as CBOT, right? And even though the product quality may be good, which is physical and chemical quality, or nutritive value may still be there beyond 10 days at 5 degrees C, but because the anaerobic spores have survived for the process of 70 degrees C, 2 minutes, this anaerobic spore could germinate at refrigeration temperature if it has survived after 10 days. So it takes minimum 10 days to germinate. So that's why the shelf life is 10 days, because you have not killed that spore. In case of sterilization, which is we completely destroy all microorganisms, but that's the book definition of sterilization, but usually we do not do that level of destruction. What we do is what we call commercial sterilization or commercial sterilized product, which is you have 12D reduction based on the CBOT. And again, spoilage microorganisms are reduced to a significant number that do not grow under the normal storage condition, and you have shelf life of 2 to 3 years. And so the shelf life for those products is not based on the microbial growth, it's based on the quality changes. Again, this is giving a chart for the thermal process consideration. So as you can see that we do an vacuum sealing of those cans or glass bottles, or it could be polymeric pouches. And if these products are high acid product, then you do not need sterilization. You can do pasteurization and then you store it refrigeration temperature. If it is the low acid product, then you do sterilization, and then that sterilization is usually carried out more than 110 degrees C. And as I said, you based on 12D log reduction of your target pathogen, which is CBOT. And of course, you reduce the spoilage microorganisms as well. Actually, 12D process is sufficient from the safety point of view, but industry tend to give a higher process than that because the spoilage is due to spoilage microorganisms, so you want to destroy a little bit more microorganisms. So the process is actually goes beyond 12D process, which takes care of the safety, but spoilage you take care based on the initial microbial load of those spoilage microorganisms in your product and how much quality changes you are ready to accept. But if you don't do sterilization of that product, you can do pasteurization of those products, but then you destroy selected pathogens and then you do the storage at refrigeration temperature, and it has a minimum shelf life, such as milk. So if you want to design a process, what you need, heat penetration data, because if you want to find the process, it means that what temperature you want to use and how long you want to process. To figure out that time temperature combination, so you carry out the heat penetration study. Basically, you take your product in a given geometry, you plug the thermocouples at this lowest heating point, and you collect the temperature profile during heating, and then it tells you how long it's going to heat and what would be the temperature during heating. And then also you have your target pathogen for which you are designing the process. You collect the D and Z value, thermal destruction kinetics, and you combine them together and you design your process, and eventually you have to microbiologically validate that process. And the way you do that, you do inoculated pack study. It means that you take the selected amount of your bacteria, put it in your food, and process, and those process design what you did before, and then have that package, open it, and see that whether they survive. Okay, so that's how you microbiologically validate that process. I think part of that call calculation we will do a little bit this afternoon or sometime during course of the short course. And these are some of the spore forming bacteria for low acid and high acid product depending upon the pH. And this is a classification based on their growth at temperatures. So thermophilic will grow at high temperature, mesophilic somewhere in between, and psychrophilic could grow at refrigeration temperature. So depending upon whatever storage condition you are selecting, you would target that bacteria for your process design. So now let's look at what are the advances that have happened in terms of the technology. The concept which I explained, those have been there 100 years. The changes what are happening, the science has not changed, but the technology has changed over the period. We have retard-based sterilization, aseptic processing and packaging. You gave some good example about it. You gave example of ohmic heating, which is electrical resistance heating, and we have the microwave heating as well. In all cases, you are heating. The way you provide the heating the food, that's the only thing different. So the science remains same. It is the technology which is different. And in this particular lecture, we will cover the top one, which is retard, but we will have one of the lectures where we would cover microwave-based heating as well. So for pasteurization, as you can see, some of these equipment, in this case, it is the steam jacketed kettle. Why do you say steam jacketed? It's an indirect heating. So you have a jacket, you have a double wall, yeah. So you could have a direct heating as well, but what would be the problem with the direct heating? Sorry? Denaturation.
Transfer of
Well, Maillard reaction is based on the temperature, whether you're giving a temperature by direct steam heating or indirect heating. The product, in order to achieve that sterilization, or in this case pasteurization condition, you are looking for that time temperature. So whatever.
Steam has more penetration power than heating.
So you understand the difference. There's a direct heating, which means you inject the steam in your product, correct? And the indirect heating is that where you have product in a container, actually you are heating container, whatever way you are heating, right? Could be hot water, could be steam, you can have, a fire, could be gas fire or electric fire, right? What would be the difference?
So if we inject steam, a particular area will be affected if it's at a very high temperature.
Well, we can spread the product, we can design the steam chamber where we could, have the exposure of your product in all surfaces and entire volume. The difference would be, in case of an indirect heating, the product is only being heated. Its composition is not changing, but if you use steam, you inject into the product, what will happen is steam will condense. And that condensed steam, which is water, becomes part of your product now, right? So if that is the case, then your product composition is changing. And if you want to maintain the same composition, so either we use indirect heating or somehow we remove that water. And how can we remove that water? Flash cooling, yeah. So you could have a vacuum and you reduce, and you could have evaporation, and then you can remove the desired level of water, what you have added through the condensation of steam. Yeah, so that was the next one. You can have the steam injection, but then you do the vacuum cooling. You could inject steam into the product, or you can have a chamber full of steam and inject the product into the steam. In terms of indirect heating, you can use heat exchanger rather than the kettle, and it could be plate heat exchanger or tubular or Shalen tube or scrap surfaces. What is a plate heat exchanger? So you have series of plates and the alternate, medium and your food product. Most of the milk pasteurization is done actually using plate heat exchanger. Tubular heat exchanger is that you have two tubes, one into another tube. The outer tube is a bigger diameter, inner tube has smaller diameter, and then you could have product inside diameter tube and the heating medium outside, or vice versa. In case of a Shalen tube, you have multiple tubes within one big shell. In case of a scrap surface heat exchanger, this is typically used for where we have extremely high viscous product, where they have tendency of fouling. Let's say if you have a milk or thick high viscosity product, let's say you are pasteurizing soups with some particles. Soup is thick, or you are pasteurizing tomato ketchup. So in that cases, they tend to have fouling or deposits on the surface, so they use the scraper to keep on scraping as you are doing the pasteurization. Retard technology is very old. How old it is? Actually, who was the inventor for canning? When did he do this first experiment? It is 1895. That's the first time he patented his process. Probably he started some experiments before that. So about 225 years has gone through in this technology. It's an in-package processing, which means that you put the food in a package first and then subject it to high temperature. It could be high temperature steam or high temperature water. And you are sterilizing food and container at the same time. And overall process depends upon type of food, whether product is conduction heated or convection heated. For example, liquid products are liquid and particles together. And it depends upon the container geometry. And whether you have the still cook, it means that containers are still, they're not mechanically agitated during processing, or you could have the agitation processing. So this is an example of still retard system vertical. Have you seen this? Yes, no, yes, no? Yes? Okay, this is the industrial version of the pressure cooker what we have at home. Only thing is there is that in this vertical steel, metal chamber, you load your containers, which means that cans or glass bottles or plastic pouches. You allow steam to inject into it, and whatever air is there, you flush it out. So you do a lot of bleeding of steam. So if you go have you visited any company, food processing company, where they are using these retards? It's a very noisy place. All the time they keep bleeding the air out from that, and in order to maintain the good circulation of the steam within the chamber, they keep bleeding the steam also. Bleeding means that this allowed to enter at one place, but they have the opening in the top someplace so that they keep losing the steam. It's a very energy intensive, not very energy efficient, and it's 200 years old technology. So, but still, we keep using. Why we keep using? Even though if they are not efficient? Because we already invested, right? So, and that is a big reason why it takes huge time to change the technology. Because if you have invested millions of dollars in your industry, even if it is a little bit less efficient, you cannot overnight, throw that. It's not like a cell phone. We have iPhone 8 and now iPhone X, so you can still throw if you're a rich person, and then you can buy the new phone. But that doesn't happen with the industrial equipment. Even if one person does that, one industry does that, other is going to buy and still continue to use. You're just not going to throw in a garbage. So we still continue to use these big monsters, which are less energy efficient. This is another version, rather than vertical. This is the horizontal system, and in fact, you can see your notes that there are different walls. Some place to inject steam, some place to take the air out. There is a safety valve, and there is a way to inject cold water, and there is a way to drain that cold water once cooling is done. So all these nomenclatures are there. This is showing the schematic of the loading system. So this is how you would lower the big basket containing all your containers into retard if it is a horizontal system. So this is how. So there is no manual stacking the cans into the retard. This is all mechanical loading. So this showing the big picture of the commercial horizontal retard. You can see that the thousands and thousands of cans are really heated or processed at one time. So even though they are batch system, you can do processing of large number of cans at the same time. This is another look where you have the control system. So actually, there's no operator standing all the time there. Control systems are now using. So these are the advances. There was a time where everything was a manual. The operators would come and switch it on, change the valves, time it out, how much is the process time, then stop the steam, then allow cold water to get in. And so everything is timed out and it's operated by the operator. But nowadays, one operator can operate, and actually it does, hundreds of retard at one time. So everything is connected to the computers and with the control system. So yeah, this is the one which is showing there's a multiple retard, and as you can see, there's no person around. So it's all managed by one person in a control room, and many times loading, unloading is also using mechanical systems, and the person sitting in a control room is just doing that. The development which has happened actually in most recent years from the two point of view, one is the heating media and other is the agitation of containers. So what does it mean by heating media? So when Nicholas Appert really started, of course his experiment was with only hot water, but then later we learned what is the problem with hot water? You can have maximum temperature of 100 degrees C at atmosphere pressure, right? So then when we learned that we need to use 120 or 110 degrees C plus, then of course you need a pressurized vessel. And then steam can give you temperature and can give you pressure as well. So steam retard became popular, and then next 150 years it was a steam retard all around the world. It's only last couple of decades, they are using different media. And what are these different media other than steam? What you can think of? What you can think of other than steam?
Cooling oils.
Hotter.
Hot air. Is it a hot air good choice?
Salt solution you can use.
Sorry?
Salt solution.
Okay, let's go one at a time. Is it hot air? What would be the problem with the hot air?
Its conductivity is low.
It takes huge effort and energy to even heat the air. Okay, so that's why we don't do much. And you said, why we would salt solution?
So boiling temperature is higher than that of normal water.
Okay, so basically if you want to increase temperature more than 100 degrees C, you can incorporate some solute which will increase the boiling. What other than that we can use? Because salt water is corrosive, and you all have a metal, right? So that's not used, but theoretically we could. So rather than using salt water, what we can use to increase the temperature of water beyond 100 degrees C? Well, you can use electromagnetic wave to heat water more than 100, but how can you have 100 degree water, more than 100 degrees C water See, if you use oil, some of the oils can go more than 100 degrees C, but then you have to recycle. You cannot drain the oil simply, right? And if oil, the containers become oily all around. How can you get the temperature of water more than 100 degrees C? Pressure. No, not increasing the pressure. And that increase in the pressure you could have from either steam or air, right? So you can have high pressure, high temperature water. So these are some of the development we'll go through individually for those media. And other is the agitation of containers. Why agitation? So you can increase the rate of heat transfer. What kind of product? Which are liquid, because they are heated by convection, right? If it is just the fish or meat in a can, agitation would not help, right? If you have some liquid, like a soup product, it's only liquid, such as, let's say, tomato soup. But if you could have liquid and particles, like a solid food, such as chickpeas in a brine solution, or meatballs in a sauce, or fish in a gravy, those are liquid and solid food. Then if you allow some mechanical agitation, you can increase the rate of heat transfer, because liquid part, you can enhance the heat transfer by having mechanical agitation and some sort of a turbulence in the liquid. For example, when we do cooking at home, if it is a liquid product, what we do, we keep on stirring. That's what you're doing. You're renewing the heat transfer surface. So the product which is heated by the pan bottom surface, by scraping it or by using your stirrer, you're removing, changing, and then new surface which is colder on the top going in the bottom. So you're allowing it a good mixing that increases the rate of heat transfer. So that's what we do, the agitation of this container in this retard. So early retard didn't have, but most modern retards now, they have incorporating these kind of agitation. So in terms of the heating media, we still have saturated steam processing. Sometimes we have steam and air. Why we had to add air with steam? I mean, just the steam by itself is good, as you can see the first one. Why we had to add air? Or when we realized the need of adding air with steam?
To control its temperature.
How do you control? I mean, steam, if you have a pressurized steam, you can just keep on increasing the pressure. You must have seen the steam chart. You can increase the temperature by increasing the pressure. You keep on adding the energy. We realized the need of including air with steam when we started working with the plastic packaging. So think about it. So how's the process? You have the retard, you load your containers into the retard, and imagine now, let's say if it is the saturated steam, processing. You open the valve, allow steam to get into the retard. Initially, there's a lot of air, so you would vent out. Open the vent, it's going to remove the air. When air is completely removed, you can close the vent, and then steam will be keep on increasing the temperature inside. Whatever temperature you have set, there will be corresponding pressure. Let's say you are processing at 120 degrees C temperature, so that will be corresponding. You can find from a steam chart, you can find what would be the pressure, so you maintain that temperature and pressure. You achieve your sterilization, and then what you want to do? You want to cool, right? How do you do cooling? You can remove the steam, but how you are going to cool? You supply the cold water, right? Imagine now in a pressure vessel, if you have a steam, if you supply the cold water, what will happen? It will condense the steam immediately. And if it condenses the steam immediately, what will be the pressure inside the vessel? Come down to atmosphere pressure, right? What is the temperature of the product inside the can? It's still hot because cooling would happen slowly, right? If the product temperature is very high inside, the pressure would be also very high inside. So now you have a high temperature, high pressure inside the can, and outside relatively high temperature but very low pressure. But metal cans are strong enough to sustain this pressure differential because, as I said, they are strong. But if you have polymeric pouches, the seal is not strong enough. They will just blow. Actually, they did, and this is how they realized that these polymeric pouches or polymeric containers, they are bursting because inside pressure is high and outside pressure is atmosphere pressure. So in order to have the additional pressure during cooling, what they do, they inject 20-25% kind of air into the steam. So they do the initial heating with the steam and air mixture rather than having the pure steam. So 75% is pressure maintained by steam, and other 25% pressure is maintained, overpressure is maintained by the air. So when you're doing cooling, actually you collapse the steam, but air would be still there. That air would exert some outside pressure. Still there is a pressure differential, but now it is much lower than if it was only pure steam. So with that sealing is able to maintain its integrity. So that's why the steam air processing came into the play. In case of a water immersion, you have a high temperature, high pressure water. Why you think we wanted to have high temperature, high pressure water? Why not just saturated steam? What's the problem with saturated steam? So in case of polymeric packaging, as I said, if you have pure steam, you have the seal strength problem due to pressure differential. So that solved the processing of the polymer-based containers. It could be can, it could be pouches. Why you think we would have realized that we need to have water immersion processing, which means the high temperature, high pressure water? The need came when we wanted to process glass containers. Now, what temperature glass can take? How high you can heat the glass? You know what is the melting temperature of glass? It is more than 1200, right? So heating the glass is not a problem really. We don't use that level of high temperatures actually in our lab, do we? We don't. I mean, of course, some chemistry lab, you can put your glass on a flame that gives you those kind of a temperatures, but in food industry, we don't have to heat glass more than 120 degrees, 125 degrees C, because that's the kind of processing temperature we're talking. What is the problem with the glass? Have you broken the glass in your chemistry lab anytime? I mean, not by mechanical breaking, but thermal damage.
They are known for the thermal problems.
Correct. So if you have the sudden temperature change, then it can crack. it can take very high temperatures, but not the sudden change in temperature. So when you have a steam-based processing, there is a sudden change in temperature during cooling. So even if you have steam air processing or saturated steam processing, during heating there is no problem. But then during cooling, if you allow cold water to come into the vessel, steam would collapse and the surface, the food may still be very hot, but the surface of the glass would be same temperature as the cold water. So suddenly from 120 degrees C, it will come whatever cold water temperature is there. So that's a big thermal shock, and glass cannot take that. But in case of water immersion processing, the way it happens that during cooling, what you do, you slowly remove the hot water from the bottom and you inject the cold water from the top. So the outside environment during cooling, the temperature of the cold water or the cooling media is also not sudden. So the temperature from, let's say you are using high pressure, high temperature water of 120 degrees C. Then slowly you remove from the bottom and add cold water of, let's say, 4 degrees C or even 10 degrees C. The temperature of the water, because it's a big thermal mass, and a huge amount of hot water is there. You slowly remove the hot water and slowly add the cold water. So there will be gradual change in the temperature. Because the gradual change, there is no thermal shock on glass containers. Because of that, we started using the water immersion processing. Water cascade is basically fall of hot water inside the vessel. And in case of a steam water spray, you are spraying. You're not filling the chamber all around with steam or hot water. You are just spraying over the containers and collecting from the bottom and then again recirculating them. So this way you can apply a lot of turbulence all around the cans or containers inside the vessel to have a very good heat transfer. So basically it was an improvement because of the containers and because of the heat transfer. So I'm going to go quickly. Many of things I did explain that these kind of a steam retard. This is the oldest method of in container sterilization. You put everything inside, close the door, secure the lock, and these are some of the steps which we've gone through. You have come up vent, you open as you're supplying the steam, you remove the air, and you have come up vent close. So once you remove all the air, you still close the valve, but retard would take some time to come to that operating temperature. So that's what is a come up. Once it comes to that step, then you are basically cooking or sterilizing, and then during cooling, it's under still high pressure. You cool it, and then so that's you fill it with the water, and then pressure cool, and then you can, once cans are a little bit cooler, you can have atmosphere cooling, and then you drain the water. So these are the steps. I guess they are self-explanatory here, so we don't have to go through. This is basically each and every step it is explaining in a little bit more detail. So this is what I said. So let's go quickly. This is very clear to you. Yeah, so this is about the water immersion. These kind of retard, they come both in vertical or horizontal models. And then basically, as I said, in these cases, in case of horizontal system, you had 2 vessels, but in case of a vertical system, you had just 1 vessel. In case of a horizontal system, you had 2 vessels. Let me see if I have the picture. Yeah, like this. So in one vessel, you have high pressure hot water, and the other vessel is for sterilization. So you open the door, you put it all your cans in the big baskets inside, close the door, and then you allow this hot water to enter into this bottom vessel. And as it is entering, it's slowly filling up. And as slowly filling up, it is giving some heat. So it's actually not maintaining 120 degrees C if this is the temperature of the water in your upper vessel. But during filling, there will be a small change in the temperature, but eventually once it it fills completely with the hot water, you can inject some more steam to bring the temperature to the operating level. And once your sterilization process is complete, then slowly you remove the hot water and fill it into your storage tank so that you can recycle this hot water so it becomes more energy efficient. And then you add the cold water into this. So you remove the hot water, store it in the upper tank, and you allow cold water to come in. And once everything is cooled down, then you drain this water out. And in some cases, the configuration could be upside down. So you could have the processing in upper vessel and these hot water storage in the bottom vessel, depending upon the design or manufacturing of those units. But most of the time, it is easier to have your processing in the bottom vessel and water storage in the upper vessel, especially commercial system. But if it is the lab scale system, then usually you have lower one is for the storage of water, and this one, because the height is not very high, a smaller height, so that at your height you can open the door and you remove the cans. But in industrial systems, because you are using machines, it is easier to remove from the bottom than the top. So this is the water immersion system. Yeah, this is some of the details how we do, that's what I explained. The overpressure, I was saying you can have using steam or you can have a compressed air. Okay, so either way you could obtain the overpressure, because if you don't have overpressure, you cannot have the water more than 100 degrees C. So you have to have some overpressure, which you can either achieve from steam or from the air. In case of a water casket system, so this is how it is, the design. So you have containers are stacked together and you allow hot water. Of course, the entire system is under pressure, because if it was not the pressure, you won't be able to have the hot water falling over these cans. Okay, so you are having high pressure, hot water trickling down through these cans and coming down. You collect from the bottom. If it has lost some of the heat, it will lose some of the heat because it will give heat to the cans and its temperature will be lower. So when you collect it from bottom, then you inject some steam into it, or you can heat it externally, like an indirect heating through the tube and double pipe or the Shannon tube heat exchanger. And then again, that hot water, you trickle it down from the top. In this case, as you can imagine, if the hot water falls from the top, it will give more heat to the top containers, and it's coming down, it will be slightly cooler. So it will give less heat to the lower cans. How you can overcome this problem?
We can have channels of falling water on 2 stages or 3 stages.
By rotating. What will be the simpler one? Okay, so if it is that during heating, these cans are receiving more heat than the bottom cans, but in case of a cooling, it will be other way around, because you allow cold water to fall from the top, then that water will get heated, right? So in terms of the cooling is also more effective on the top and less, so this will have less rate of cooling. So actually the lethality achieved by is nearly same. So you need not really worry too much. So if you have the cold water coming here, what will happen to cold water? It will pick up the heat, right? And when it comes down, it will be hotter, that water. So the cooling of the cans, as you go lower and lower, it will not be effective, right? So if the cooling is not effective, it means it is receiving more heat. This is quickly cool down. So for example, if it is 120 degrees C, right, if the cold water falls, it will become 110. But then cold water, when it is falling here, it is, let's say, 10 degree. But when it is coming here, it is maybe 50 degree, right? So in that one pass, this can may come down 120 to 110, but this, because the cold water temperature is 10 degree. But here the cold water temperature is probably 50 degree. So it will not come down from 120 to 110 in one pass. Maybe it will come down from 120 to 115, right? So the cooling is slower here. So heating is faster here and slower here. So cooling is also faster here and slower here. So it compensates at a large extent. Make sense? Yes or no? Okay. Yeah, so that's what it is explained here. And then of course there's a lot of configuration, how many number of holes you could have or the size of holes as you're trickling down the water. So depending upon the can size, how big is your retard, but of course you want to have the design in a manner such that almost all cans are being exposed to this trickling down water, because if any can is not exposed, then it will not be sterilized and then you will have a problem which can is not. So you want to make sure that all cans are exposed to this hot water and there is no dead spot within that geometry where can is not being heated. And it says the cooling and heating media actually flows parallel to the main heat transfer surface. So in a can, the heat transfer surface is the vertical surface. Of course, there is some surface on the top and bottom, but most of the heat is on the sides, right? So as your water is coming down, it is going parallel to the surface, which is making very effective in terms of the heat transfer. So this system water cascade system is suited for cylindrical cans and glass jar which are standing vertically. But if you have, imagine pouches and tray which are flat, so if water falls there, what will happen to the water? The tray which is beneath the upper tray, it will not really experience that falling down water because water will come and go on the sides. So the top surface will not be exposed of those trays which are not in the first layer, second, third, fourth layer will not be exposed. So this configuration is not good for those kind of container geometry. So it says, that's what I was explaining, containers at the top heat faster than those at the bottom. First container to contact this water absorbs much of this heat energy and then you would have less, but there will be some balancing during cooling. Steam air processing, as I gave example, was considered when we wanted to process plastic-based containers. Either could be pouches or it could be cylindrical cans but made of plastics. And it says they are more common in less common in US and more popular in Europe. And this steam is injected at the bottom of the vessel. You combine with the air which is already trapped inside, and then you can use fans to circulate air within the vessel. I think I should have one picture here. So this is what it is. So in this case, it is flowing through the steam one end to the another end because you have the fan. And this fan could be positive pressure or negative pressure. If it is positive pressure and the fan is here, it will go this direction. If it has a negative pressure, it is basically sucking the steam and air from this end to this end. So these kind of retards are ideally suited to the flat containers because as you can see that the containers are lying horizontally and you are having the heating media flowing from one end to the another, front to the back or back to the front, then the heat is flowing or the heating media is flowing in a horizontal direction. So if you have the containers which are horizontal, then this heating media is parallel to the heat transfer surface. That's where you can expose all the surfaces to heating media. You don't have any resistance to that heat flow of the heating media. So that's why they are more suited to those kind of containers. And fans are draw medium towards them, so it's basically negative pressure. And in case of steam and water spray processing, this is very versatile. You both use in US and Europe. And in this case, you have the process vessel is filled in the bottom of the retard, and process water is drawn from the bottom of the retard. And you add indirect heating to redistribute this steam water spray. So for example, when you spray steam water, it will give heat to your container. Temperature will go down for a steam and water. Then you can use the indirect way of adding heat to this steam water mixture and then redistribute. So you can collect that steam water from the bottom, which has a lower temperature than which is coming from the top, and then add the heat and then recirculate them. And this direct injection can create the turbulence of water which is exiting from the spray nozzle. and then it can create a very homogeneous temperature distribution inside the vessel. And the heating creates the overpressure environment similar to what you have steam air retort. And overpressure, you can add either compressed air, and it says vent excess pressure out from the shell, and key features are ability to take the processed water and spray it, distribute throughout throughout the retort. So basically that system, rather than using vessel which is filled with saturated steam or filled with air steam mixture or completely filled with water, in this case not completely filled, is like a cascade system, water cascade system. You are just throwing hot water into it. In this case you have hot water as well as the steam together. So this is the example, steam and water spray. So you are atomizing this, you are throwing it nozzle from all around. In the bottom you collect, and then you add the heat into it, because as you spray over this container, they give heat to the container, and when what you collect from the bottom, it is a lower temperature. Then using the indirect heating method, or using some heat exchanger, you add some heat to it and bring it to the process temperature, and then again you spray all around through this vessel. So in this case, as you can see that these spray are overlapping. Because it is overlapping, you don't have any sort of dead spot where water or steam is not reaching. Because it is extremely important that each and every container receives the minimum amount of heat for which we have designed the process. Some containers may get overheated a little bit, for example, around the edges, but then inside cans should get minimum lethality for which we have designed the process. In case of agitating retort, the interest was basically to agitate or shake the content inside, which you can do with the liquid products, or if you have liquid and solid product, both. So that's the basic motive, and let's see what kind of agitation we have. So this is the end over end agitation. So for example, if you have, this is a cylindrical can in which you leave certain head space, which is the bubble kind of, it's a vacuum bubble because you suck out the air. And then as this vertical can in the cage, and the cage is rotating in a radial direction. As it is rotating, this can is actually rotating in this fashion. As it is doing, this bubble, because it is a vacuum, that always stays on the top. It's a lower density than your food product, right? So that stays on the top, and that creates the kind of turbulence or agitation that allows good mixing in the can content, and that facilitates the heat transfer. So that's the basic motive of having agitation. So this is the end over end rotation. You can, this is another picture of that, and this is ideally suited for the cylindrical vertical standing either glass jar or metal cans. The other concept was the axial rotation. So in case of axial rotation, in case of an end over end, you have vertical cans, it is going like this. And in case of axial rotation, you have vertical can is horizontal and it is rotating like this. The way it rotates is that you have very horizontal, very long retort, and in that, on the vessel, there is a cage going spirally from one end to another end. In that spiral cage, you have a can which is fixed in this, and it is kind of a rotating, and that rotation is like along the axis. So that's why it is known as a axial rotation. So you feed from one end, it goes through the spiral top of the retort and comes out the other end. And then during cooling also, it goes from the, so in this case actually you have retort in pair, one for heating and other for cooling, then heating, cooling like that. And from one end, one retort, it goes to another retort for cooling. There are pressure locks where you do not allow the cooling medium to mix with the heating medium. So this is how they have the transfer mechanism, and then they move can from heated zone to cooling zone. So in both cases, the engineering design is different, but the idea is that you are allowing it some movement inside the content of your can. And of course, you can use all kinds of temperatures and geometries, sizes. Another advances happen in case of can processing or canning. They have the hydrostatic sterilizer. So as you can see, there are huge vertical columns. As you can see here, they are like a 10 multi-story building. In that case, the red zone, as you can see, these are the 4 columns. 1, 2, 3, 4. In the second column, as you can see that this is really the steam, right? And then the green one, as actually you see this is hot water, okay? And this hot water column, is creating hydrostatic pressure, right? You understand hydrostatic pressure? The pressure created by the water column, right? So that pressure, because of that, you are able to maintain this steam more than 100 degrees C, because this steam is now under pressure. And that pressure is being created by this water column. And then this is a hot water, but this side white and this side blue are low temperature water. So then using the chains or the conveyor belts, you allow can to come in that belt, and this belt is not running horizontally. It is going vertically up, coming down, then going up and coming down through these water column or steam columns. So the cans would come. So maybe let's say can comes from this side or this side, and then it goes up and then goes in this hot water, slowly getting heated, and then goes to the steam column, it's getting heated, then comes out. This water temperature is lower than steam temperature, then it's slow cooling, and this blue one is cooler than this green one, so eventually cans are cooled. Because of this gradual increase in temperature and decrease in temperature, this is very, very suitable for in what kind of a containers, materials we need gradual change in temperature? Glass, yeah. But you can use metal cans and other type of containers as well. Yeah, so this is what all description is given, and in the end the chain speed is determined by required sterilization time. So in this case, as you can see, the vertical column length is fixed. You cannot change. So if you need a higher process time, so if, for example, if the can size is bigger, it will heat slower because now you have more volume or more mass in the cans, and the distance from the surface to the center of the can has increased. So the heat transfer will be slow. So you would need a higher process time. In order to get higher process time, you would reduce the speed of the belt, so it would spend longer time inside those columns. So this is how you can manipulate or adjust the process time. Yeah, it has a lot of different features. It says that you can have processing of cans or containers 60 to 2,000 containers per minute. The energy consumption is less, and of course little floor space is needed because everything is vertical, and sometimes it's advantageous. Why vertical space is advantageous? Well, whenever you buy land, you pay for the horizontal space. You don't pay for the vertical space. So if you can build some equipment design in a manner that it is occupying the vertical space, not the horizontal space, of course it would be less expensive. It's very reliable and high efficiency system. Then we have another retort where, so in that case also, as they are going up and down, there is some agitation because there is a movement. The another technology which has come recently in commercial area, it is the where you would have, rather than end over end or axial or going up, you would have horizontal motion. And this is particularly useful for tray and pouches, because in case of a cylindrical container, you have a head space, and that head space allows agitation when you are rotating end over end or you are rotating axially. But if you have a pouches, most of the time in pouches, we do not have actually even head space. It is completely vacuumed, and and it occupies all the volume inside the pouch. If that is the case, then imagine how would you create, if there is no bubble, how would you create the agitation? And especially if you have liquid and particle, right? Let's say chickpeas in a brine solution, or fruit pieces in a syrup, or meatballs in a gravy. And if you had to create the relative motion between two products to allow faster rate of heat transfer, how would you do that? So they do it in this kind of geometry, where you would have lay horizontal your pouches or tray, in which you would have the liquid component of your food and the particle. And when you are allowing this horizontal motion, the effect of forces on these two is different, because the density difference between solid and particle will allow different amount of force exerted on those. And if a different force is exerted, then they will have the relative motion. If liquid, imagine if you have particles suspended in a liquid, we allow different amount of force to the solid and liquid. So one will move higher speed and other will move the lower speed. And because the relative difference between the speed, they would have the kind of a mixing effect. If both are moving at the same speed, then you would not have the mixing, right? And it is in a reciprocating fashion. It goes this direction and then it goes this direction, this. So this way you allow the mixing of particles into liquid, and that enhances the heat transfer. And this is particularly suitable, as I said, for the flat type of containers. It could be pouches or trays. So this is all I have for this lecture.
Sir, slide number 25.
Okay, let's see. Yeah.
Can you please explain the process, because middle portion, how that will be exposed to?
So there is some gap. So these are the trays, you know, the carrier. So imagine how we would put trays over one over the. We will not put one tray over another tray. No, it's not. So it's a carrier. So you will have one metal carrier. In that metal carrier, you would have, let's say, if it's a small carrier, you have 100 trays, right? And then on that, you put another metal carrier. On that, you have 100 trays. And between two metal carriers, there is a gap. It's like you put one chair over another chair, you would have a gap in between. It's not one chair sitting over another chair completely. So there is a gap. So as you can see, as I point this pointer, there is a gap here.
So compared to outer periphery, middle portion will be getting less exposure to steam.
Yes, relatively less. But because, you know, I mean, this is a schematic. You would have probably hundreds of nozzles here, really. So then a lot of, you know, water and steam would be actually going through this. But you are still right. In this case, even though there is a very high degree of uniformity, but it's not mathematically completely uniform. So then what normally we would do, we would put the thermocouple in this pouch or the tray and collect the heat penetration data for this. And we'll make, okay, if this pouch or tray is sterilized, then all others also sterilized.
That time overexposure will be there in the outer periphery.
Correct. So there will be some exposure. That is true actually in any retard. When you have a large number of cans into the big vessel, from one end to another end, top to bottom, there will never be complete uniformity. But that's a limitation, and you can consider. I can make a smaller one having better uniformity, but then the throughput for the company would be very, very low, and they become very expensive, the whole process. So they try to have the fans inside that recirculate the media very effectively, or try to have multiple nozzles so you can spray and cover as much area as possible, so you create sort of a minimal non-uniformity, or you reduce the non-uniformity.
Sir, talking of steam air processing, you were saying that steam and air mixture is injected into the retort.
Well, you could inject or you could utilize the steam air which is already present inside. Either way you could design, yeah.
When we have to vent out the steam after processing, we can do one thing, that rather than introducing the water first, we can introduce the air to means to balance the pressure. In the same time, the steam will be ejected, and then we can put water into that so that pressure difference won't be there, and the pouch will not burst.
See, theoretically it is possible, but imagine, let's say you have a steam air mixture, you are taking out a steam air mixture and injecting air to maintain the pressure. That's what your argument is, right? That's what you're suggesting, yeah. See, when you exit the steam and air, what you will do with the steam and air? You won't be able to recycle it because the steam air mixture, you need a large volume, to hold that. But if you allow it cold water to enter, steam would condense. Then you will collect that steam as a hot water that you can have in the vessel, and then that hot water you can indirectly add the heat to again make it steam. So you can have recirculation of the energy. But if you just take it out, a steam air mixture, then you have to store somewhere, and gas or vapor occupies much larger volume than the liquid. So the handling would be an issue, but theoretically it is possible.